All right, welcome back. Today is our distributed system lecture, and this is a place where I can remind you of this, that we're kind of doing this on purpose. I'm doing essentially all of distributed systems, or a relevant chunk of distributed systems, in a single lecture. So this certainly will not replace a full lecture or a deep degree in distributed systems or in database systems. The whole point here is to give you an overview of the main concerns, the different strategies, the trade-offs between them, so that you can know when to ask an expert, what questions to ask, how to interact with other people. Right, so it's intentionally providing an overview and also showing you a couple of buzzwords that might be helpful in an interview at some point. So if you're thinking about scaling a system, like this was a graphic or a meme that was shared in the beginning of the pandemic about Zoom adding servers because suddenly they had such a massive demand. Do you know any other stories of what's sometimes called catastrophic success? So you're so successful that you overrun with demand and you suddenly need to scale your system and you weren't really prepared for this? Some college project that actually could scale, but it was expensive. Okay. Any other projects? Something with a wait list that you couldn't get an account because everybody else wanted to get an account at the same time?
Steam was where it crashed and
Okay, Steam, when a specific game was released. I think OpenAI, when ChatGPT came out first, right, it was hard to get an account because there was so much demand and they had to scale massively.
Would you count Obamacare, or was it just bad engineering?
Obamacare, maybe more bad engineering. That was maybe very predictable what load you might get. Anyway, when it comes to scaling systems, I think we generally know three different strategies. More efficient algorithms, faster machines, and more machines. And the first two things only get us that far. We already probably got most efficiency out of most algorithms that we're using regularly. Faster machines get faster, but they also get very expensive very quickly. So I think what we're almost always doing is using more machines, and that's why we have a distributed system problem. Today, let's talk about Google Photos as an example and applying machine learning there to index images so that you can search for things. So they run an object detection model in the background. You're not actually tagging your own photos. But you can search for objects that are in photos more or less reliably. Right? This is for how a long time I found my vaccine card when I needed to show this. Right? You just search for it, and it works reasonably well in images. Does somebody know what scale Google Photos operates on? It's probably, that's really catastrophic success if you get there very quickly. So I think none of your machine learning projects probably need to scale at that end, but I think it's still interesting to kind of think through how would you build something at that scale. Rough estimate how many users they may have? Just rough guesses. 1 billion, that was 2019. They don't actually release numbers. Well, they haven't released any numbers in a while. 2019 was the last time when they said about 1 billion. How many photos do they get per day? More than 1,000? More than 1 million? More than 1 billion? Again, I have only very old numbers. This is 2017. This was 1.2 billion photos a day. That's 14,000 photos a second. That's about 40 gigabytes of photos a second that get uploaded. Do you know how fast you can write to disk? It's about 1,000 disks in parallel that you need to write, just to write photos that you're receiving, right? Without any redundancy, 1,000 photos in parallel, and then you haven't done any model inference, right? So I think I'm sending you, for your movie recommendations, about 2 to 4 requests a second right now, and it might go up to about 10 a second. They get 14,000 requests a second 10 years ago. Right, so if you want to run inference over this, let's go back to our strategies, right? More efficient algorithms. Can we scale object detection that we can run 14,000 detections a second? Probably not. We already have fairly fast object detection mechanisms. Like a lot of models are in the milliseconds area. Faster machines. Yeah, maybe you can get a faster disk drive that writes faster than others, but not at 40 gigabytes a second. Not even close, right? The best disks you can buy. So really the only choice that you have is machines. If you want to index those photos, how fast does your model need to be? Just for a practical application. Would users need the photo to be indexed immediately? How much time do you have realistically? Just estimates, there's no correct answer here. Does it need to be milliseconds?
At least a few days so that it goes out of view from the order of photos that we do.
So the photos that you've uploaded in the last day or two, maybe you still have in mind, so you could find them. Unless you upload 1,000 photos, maybe you still want to search for them, right? But you have some time to think about this. I don't know, a minute is probably fine, 5 minutes is probably fine. A day seems long to me, but you could probably justify it if you have an outage and you catch up after the day. Right? So you don't need to do this immediately when a photo is uploaded. You have some way of doing it later. How would you design a system like this? Any idea? Any prior knowledge in this space?
Every time you photo like there's a meta measure, so we can like publish that.
So I'm more asking about how to really massively scale this processing, right? So yes, we have a lot of data. We have metadata with the photos. We can write this to a database, or immediately when, let's say there's a REST API for uploading the photos, we can immediately, when we receive an image, run the object detection mechanism. Does it seem like a reasonable design?
Maybe you could use something like a messaging queue to like store photos before they're written to disk and like one at a time.
So use a messaging queue to store queue photos. Why would you do that?
So that you like, so even if the system is overwhelmed with like a bunch of writes to the DB, you're not writing everything at one time. You're not attempting to write everything at one time. You're doing one at a time based on whatever you get from the queue.
Right. The database you probably still need to write, right? But what you're talking about is that traffic is not necessarily uniform, right? You have peak hours, and you can try to scale your inference with that, but maybe the inference part, the object detection part to index the images is not the most crucial thing, right? Write it to disk and process it later is fine if you can catch up in a minute, 5 minutes, even a day if necessary, right? So some sort of queuing system, you already know Kafka, so you could write this into a queue like Kafka and then have a processor that goes over the queue in near real time. And we come back to this as a design process, and then we can think about how to scale it there. Right. So in machine learning systems, we have often a lot of data. I think it's pretty obvious. We have the training data is often pretty big. Input data, like inference data, like the images that people are uploading to Google Photos can be very big. Telemetry data can scale quite a bit if you're collecting this from a lot of places. The models themselves can be quite big. For all of these things, we need to deal with data infrastructure and need it to be often quite scalable. Not every system needs to be massively scalable, but a lot of systems we want to scale eventually, and data can be a bottleneck. And we have large data processing tasks, like in training, we need to store, clean, and update training data. We have the learning process, which itself is often distributed across many machines. Inference, if we need to do this at the scale of Google Photos, right, we actually have to think about how do we run inference 14,000 times a second. And then potentially do requests over very large computations, large data sets, summarize things. So in the end, we distribute pretty much everything. We don't usually buy supercomputers to do things. So we do distributed data cleaning, distributed feature extraction, distributed learning, distributed predictions, incremental learning, and also distributed logging, telemetry, and so on. So let's start with storage. This is kind of database basics. If we have data that's too big to fit on a single disk, or data that's too much incoming data to write to a single disk, what can we do? There's two fundamental strategies, partitioning and replication. Which one, to the degree that you either know this already or can guess from the name, what are those and how do they help with scaling?
Replication is with regards to durability of data, so the same copy of data is stored at multiple places.
Right.
To make sure that if one node fails, the other nodes still have that.
That seems to not help with scalability. It actually makes it worse, right? Because we need to store everything 2 or 3 times for redundancy. How do we actually scale?
Using partitioning, we can determine certain factors on the basis of which we can split the number of requests incoming into different servers, like a distributed processing.
So with partitioning, we split data in some way, right? So partitioning is the idea that you split your entire data set and store different parts of the data in different places. There are different ways to partition things. Can be pretty much random, or you can do it by geographic regions. You can potentially also partition by column in a database so that the photo metadata is in a different machine than the actual photos. But partitioning is just the idea that you divide your data and you don't keep it all on the same machine. You store it on different machines. So if I need 1,000 machines just to write to disk concurrently the incoming things for Google Photos, I need at least 1,000 machines to receive the requests and write them to disk. Probably more, right? I can't have a single machine. Probably 1,000 machines is not enough. So we have a lot of machines working in parallel. And we partition the data so that we write to any one of those machines. So we have replication as a form of redundancy and partitioning as a way of splitting things. Partitioning actually helps us with scalability. Why do we need replication? And how do they relate to each other?
So we can read from like various machines.
So, right. So replication helps with read throughput. So if you're reading a lot, this actually also helps you with scalability. We have the same data on many different machines, so we can read in parallel from different machines. Let's say we don't care about read throughput that much, not to the case that what are other reasons that we replicate data if we partition it?
Tolerance. Fault tolerance.
Fault tolerance. Why do we need that? Why do we need this more when we partition data?
Well, because the data is split up into different places, if we are already going to different places to access it, and one of them goes down, we won't be able to recreate it in the future.
Right, so fault tolerance is the main argument here. If you split data that way, in this case you have 3 databases or 3 disks. The chance that any one of them goes down is suddenly 3 times higher than if you only had a single database or a single disk. If you're writing in parallel to 1,000 disks, it's very likely that one of them crashes in a day, right? So you suddenly have many, many points of failure that can lead to losing data, much more than if you had everything on a single disk. Then you might gamble, right? If you have 1,000 disks, you don't want to gamble anymore. So it's very natural that the more you partition data, the more you add replication to the mix, just to have some redundancy, because you have so many points of failures that you don't want to bet on any one of them. So it's usually common to have some balancing strategy between replication and partitioning. We need partition to just deal with a massive amount of data, and then we add replication for some fault tolerance. Typically have each data at least in 2 places, maybe in 3 places. Typical RAID systems do this transparently for you in the background across multiple disks. And lots of database systems and other kinds of systems will do this for you across many different machines. This is typically not something you implement yourself. This is actually, for most of the things that I'm going to talk about today, we use existing abstractions. You can take a distributed systems course to really understand how this works underneath, how a RAID system works, or how a distributed consensus protocol works. For our purpose, we often use existing tools, databases in this case, that already support that functionality. It's useful to know what the underlying concepts are, roughly, that you know which database to pick, for example, or what to look for, or that you need to enable replication. But you don't really worry about this in an implementation level, typically. And so most database systems will allow some form of partitioning out of the box, or with very little configuration overhead, and some replication too. The problem that always comes with distributed system is, how do you synchronize data? How do you deal with consistency across multiple machines? The standard model for replicating data at scale and also dealing with redundancy is a follower leader model, where you have one leader and many followers. The leader knows where the data goes and what the right version of the data is, and all the followers have copies of all or some of the data. So whenever you write something, you see this here, you contact the primary database, you write to that, and then the secondary databases, the copies, the replications, they get updates in a delayed fashion, often pretty quickly, right? But they might be slightly behind. You don't get inconsistencies beyond being behind, because everything goes through the central primary database. What's the obvious drawback of this system?
If the leader fails, then the writes won't pass.
Yep, that's one drawback. The leader is a single point of failure. Anything else?
The application is not synchronous.
What do you mean by the application is not synchronous?
As in, the processes are in async, like you can copy data.
So you might be slightly behind. You have a slightly outdated version, potentially, of the data. Yep. Another obvious drawback?
It will take more time at partition.
What takes more time?
More time at partition.
Why does it take more time? Sorry, why does it take more time to process? All right, so you have a bottleneck in the leader, because all the writes go to that one leader. So even if you can replicate it and have easy reads from many different databases, the writes still go all to one place. Right, so you can partition again on top of that and have multiple leaders for different parts of the data. You can do this. But there are many different database systems that have a different architecture where you can write to different nodes. This is kind of a design that works pretty well. It's pretty easy, but it doesn't scale if you have lots of writes. For something like Google Photos, where you write 50 gigabytes a second, you wouldn't find a single machine that can accept this kind of data. Pretty much all standard database systems support this form of replication, just kind of copying things. That's your Postgres, your MySQL, your MongoDB, and so on. Google File Systems, I've shown you this earlier, has a slightly different strategy where the central server just knows the files and where they are, but you directly write to one of the many chunk servers. So you don't want to all write all data to this machine. You just say, I have a new image here, tell me where to write it, and then the actual write goes to a chunk server. And these are massively right? They are partitioned a lot, and you have some redundancy a lot where each file is also in multiple locations. This is a central point. At least all lookups go through that place, right? Or if you want to write a file, you get a handle and the location from that space. And I suspect they have a way to distribute that and make it fault tolerant too. There's a lot of strategies to go beyond that that usually have to do some trade-offs on consistency. If you can give up consistency a little bit, there's lots of things that you can do to scale a little bit better, and I don't want to turn this into a full database lecture. But there's multi-leader replication, where you essentially can write to any of multiple machines. You typically write to multiple machines at the same time, and then when you read, you fix things by reading, by checking multiple machines and see whether you can reach consensus. And if you have inconsistent writes, where one machine has one different value than another machine, you need some sort of repair mechanism later. And leaderless replication, you give up on leaders at all. This is how Google Docs works internally and systems like this, where if you go offline, you can continue editing, and if you go online again, it synchronizes with what somebody else has changed. So this has essentially deltas and tries to figure out which delta came before one and merges them. And worst case, you have some conflict, merge conflict in there, and then you need to figure out what to do. Google Docs just does something. I think you might lose some data in the process. If you use something like Dropbox, it will keep copies, or Git with a merge conflict will show you this quite explicitly. They usually have versioned so that they can go back and see what the deltas and the changes are. You have a clock problem, and these are all pretty standard distributed system problems. For the purpose of this class, is really just, if you have more data than fits on a single machine, start thinking about replication and partitioning, and then figure out what database solution works for that. Right? Leader-follower models are usually simple, and most systems follow that in some form. You almost never need transactions, I think, for the kind of systems that we're thinking about in this class. If you not do banking software or something where the value really precisely matters, like if you have inconsistencies between object detection on a photo, like if you read it one time, you get a different object than another time, it probably doesn't matter. You want something close enough. Merge conflicts is probably the union of all tags is usually good enough. So in a lot of systems, when it doesn't need to be that precise, makes it much easier to scale. If you really need precision, distributed transactions are a pain to set up and usually pretty slow. Any questions on this part? With this, I want to go through three main strategies of how we scale systems. Services, batch processing, and stream processing. And then at the end, we come to the obvious combination of those. With services, you may have seen microservices. About 10 years ago, this was a big hype word. Everybody was talking about this and introducing microservices. In a way, it's really simple. It's just remote procedure calls between machines. So the movie system asking your recommendation engine to give me a recommendation over a REST API, over an HTTP call, that's how you call a microservice, right? In a way, your recommendation engine is a service, and I'm making requests to that, and you respond immediately. Microservices or services generally work like function calls. I make a request, and I wait for the answer. It's just a distributed function call, so I may never get an answer, and then there's some timeout mechanism, right? Or somebody may attack this over the wire. It was called microservice because people made fairly small services. Originally, software was often a big piece of software, and we didn't want to split it into many small pieces. You had maybe the rendering engine for the movie platform in the same place where the movie recommendation is, and if you need more scalability, you copy the entire system on a different machine. The idea with microservices was, let's break the software down into smaller components, just like we already do this with modules and submodules. It's just, now let's do this over the network with HTTP requests. So we have relatively small services that are all small web servers that we can make HTTP calls to. And if we need more copies of one of them, we just replicate them, right? So if, I think I showed you this briefly earlier, if we need more caches, we just make more machines just of the caching without replicating everything else, right? If we need more asset metadata, we make more copies of this one rather than replicating the rest of the machine. Another benefit is also that you can use a different technology stack for each of these components. Your movie recommendation service, I suspect most of you wrote it in Python. Did anybody use anything else? The rest of the system is written in Scala. I assume you didn't want to write it in Scala, right? And learn a language that's maybe not the most popular language anymore. Just the one that I learned when I did my last big programming task. This allows you to write different parts of the software very easily in different languages with different technology stacks, different teams. You just agree on the interface between them. You can scale them independently. And microservices, it's micro because the functionality is often pretty small. Right? It's often something like account management or these kind of examples. I have a picture here of the actual, or some version of the actual Netflix architecture. So that's very abstract. It's not very helpful. You usually have fairly small functionality. And then each of these things ideally has its own state. So each of these services has their own database. Like you have your own database to collect training data, train a model. This is part of your service. If you really need to share data across multiple services, you can do something like this, where you have a shared database and multiple versions of the service that might run on different virtual machines can connect to the same database. And ideally, you have separate partitioned databases for these services. The main problem with microservices is that you now have a distributed systems problem. Before, everything was easy. You called functions inside your software. When you call a function in Python, you don't need to worry that the network goes down, that you don't get an answer, that there might be a timeout or similar things. Now you have all the classic distributed systems problems. You make a call over the network. You hope that you get an answer. You may not. You may not get an answer in time. The network might be slow. There might be replicas, so you might go to one of multiple machines. So microservices add a lot of extra complexity to actually manage them well. Typically, we don't just use standard REST API calls with the request library or something like this because we need so much overhead for monitoring to figure out when something goes wrong. There's a lot of load balancing and routing infrastructure typically, so that you often use specific libraries just to deal with this massive complexity from distributed systems. This is an example of a gateway pattern, a common way to think about managing complexity in microservices, where you have this extra gateway in the middle. The client just talks to this gateway, and the gateway deals with permissions, it deals with caching, it deals with logging, debugging for performance, and it can also translate different API or like this service might just speak XML, and it translates it into JSON over here, so it can do this kind of conversation and make it have a central lookup mechanism. There's usually a lot of infrastructure about scaling and auto-scaling all of these components. If you buy into the system, you find a lot of tooling around this. If you can avoid it, I would avoid it because it adds a lot of complexity, but it's a way to scale. Actually, in recent years, a lot of companies switched back from microservices architectures to something more monolithic because it reduces complexity. I think it trend more recently. Any questions? Who here has some experience with MapReduce or similar batch processing infrastructure? Not that popular anymore. Quite a few do, but not the vast majority. Batch processing is the kind of work where you do massive, large jobs over very large data sets, often data sets that don't fit on a single machine. And this might run for an hour or a couple of hours across many different machines. How well can you read shell scripts? What's this code doing up there? So the first line is putting out line by line a log file from some web server in this case. The second line takes a single column of those, so it extracts information from that. In this case, it's a file name. So you get a file name, a list of file names that the web server accesses. The next line, I guess it's obvious, is sorting the data. What does unique C do? It's sorry?
Remove duplicates?
Yeah, that's what it does without the -c. What does the -c do? It's counting how many duplicates there are. So it's counting, so by first sorting and then counting unique rows in a row, duplicate rows in a row, you count how many times each file is in the log, essentially. And then we're sorting it reverse numerically, and then we're putting out the first 5 lines. In general, what does this code do? What's the intention? It looks at the most viewed files on a web server, right? So in the log file, which files have been in the log file the most? So you can look at which files have been viewed the most or opened the most. And it does this through multiple steps. So it breaks this kind of computation of counting into a sequence of steps. This is a Unix way of doing small programs, right? Command line, text in, text out. Before we're sorting, we're just extracting the files. So the amount of data that we're sorting is smaller than the original data because we already extracted the files. And then unique is this very small reusable operation. We're sorting this again, and we're just looking at the top. Right, so we're doing computation step by step. MapReduce is a very similar idea to just do this across a distributed system. Let me show you kind of example of how you might do this at massive scale. So let's say you have many web servers, and you want to also know the most popular files, the most popular images. So we have log files on many different hard drives or many different machines. So what we can do in the first step is extract how often is a file shown on each machine separately. So this is easy to parallelize. It's like the first step, the AWK, like extracting all files. And then we can count them also separately. Like the sorting and unique, we can do separately on each machine. And now we need to aggregate data across multiple machines. Right? We have the intermediate summaries on each machine. And the next step is merging this from multiple machines together. So in MapReduce, the first step is called a map because we're looking at one line at a time or one data chunk at a time. And then reduce is doing some operation on this. There's a shuffle step in between that's merging data from multiple sources. And we don't want to merge all data at once. So what we're typically doing is shuffling this or merging this by buckets. So for example, everything with image, I don't know how this was done, image 13 is on one machine. all the other images are on a different machine. So we're sorting these lines according to some hash function so that the results from multiple machines relating to the same image arrive in the same bucket. Does this make sense? Right, so we want to avoid bringing all data together on a single machine. There might just be too much. So we're merging this chunk by chunk. And then when we brought it together, we can do more operations like counting. This is like the unique sort kind of thing. And then we can repeat this step again, right? We do operations on this data set, and then we can shuffle again. We can do more operations. We can shuffle again. The whole idea of this is really to scale operations across multiple machines and to avoid sending data over the network as much as possible. Computations on a single machine are usually much faster than network traffic, sending massive amounts of data across the network. So what we want to do is reduce the data as much as possible locally, run enough computations locally, and then send only the results. And if the results are still too big for a single machine, collect them in multiple machines, do more processing, narrow it down further, send as little data over the network as possible. The MapReduce way is often described as it's cheaper to move computations to the data than moving the data to the computation. There's a lot of infrastructure here for this. Hadoop is a common open source framework for this. There's several others. The main functionality that this has is we have these large computations that run on many different machines. Any of those may crash at any time. We already have replicated data, so we can choose where we run things. So we have this infrastructure, Hadoop, or the MapReduce infrastructure at Google, that essentially manages these long-running executions. If a machine crashes, it tries again on a different machine. We wait for it for a while. We wait until all the data has arrived in the shuffle step, and then do the reduce operation on this. These computations can run for hours. Some machines might be busy, some machines might be slower, some network parts might be briefly unavailable, and also the computations usually run over massive amounts of data in parallel. So the whole point of this is to do really massive distributed operations. Like if we need to look at every single image in Google Photos, let's say we have a new version of the object detection model. We want to apply this to every single photo that we have, not just the new incoming ones. We probably need something like this. We don't want to send all the photos to a single machine and send it all over the network. The model is much smaller. We move the model to the storage where the images are, and then we run them locally over this. And if we run some analysis, like see how many dogs are in the images, then we can look at some aggregated results and merge them back together. Make sense? The key point here between services and batch processing is services give you an answer immediately, and you can run many things in parallel to give you an answer. You make a method call, you get an answer. Batch processing, you typically start a large job over large amounts of data, and you may get an answer an hour later or a day later, right? These are long-running things that run across many different machines, large data sets. So it feels a little bit like breaking it into smaller tasks like the shell commands. Where would you use this in machine learning? What kind of tasks might you run over large data sets locally at the data? I mean, inference over all your data is one example. I already told you that, right? Move the object detection to the images. What else might you run over massive amounts of data? Data cleaning, data feature engineering. If you're extracting features or if you're extracting things from very large data sets across many different machines, right? So this you can process often in parallel, right? Each row in parallel. Yep. Distributed learning in general runs, like the parameter server architecture, what's behind TensorFlow and so on, runs somewhat of this in parallel. Not quite in the same way, but you learn locally with each data set. And then there's a way to just merge the weight updates essentially for the model. So we use this kind of thing for all kinds of long-running processes. For example, when I created the self-descriptions of your movie users, this was extremely slow when I called the, what LM did I use? Claude, one at a time, right? There's a million users, one at a time. I looked at this at some point. This would take 30 days to compute. There's a batch processing step that I could use. This was from Google directly. So you can upload all your queries at once, and then Google runs them at their leisure. It actually also took a while, but it took more like 8 hours. And you could see progress, and it was varying depending on how busy Google was with other things, I assume. So it wasn't a very linear process. But it's this kind of thing where I don't really worry that much about how fast an answer is. If I want a single prediction, I make a call directly to the model. If I want a million predictions, I can do this in a batch process and get the answer a while later. It's still much faster than doing this one at a time because they can decide how to distribute this, and also you don't do the back and forth network traffic, right? It's much more efficient. You may have seen some more modern data flow engines. They were very popular for a while. I don't think they are as much, as we're not training models that much anymore. They're like fancier versions of MapReduce where you have more flexibility and nicer data structures, but it's a similar idea. And again, this is, I think, the key idea behind MapReduce and similar approaches is moving the computations to the data. Don't move the data to the computations. All right. Last one is stream processing. And you have a flavor of this, although you're not using it a lot, through Kafka. Kafka is a good example of this. And you mentioned this earlier as a way that we could do this with photo indexing. So the Kafka topic is essentially a stream of events. You probably notice, or maybe you haven't noticed yet, you're losing the oldest messages in there. It's not an infinitely growing file. It's just the most recent events that are in the stream. Some stream processing software delete data as soon as it has been processed. Kafka typically has a storage limit or age limit and then automatically prunes data at some point. So you could have the photo uploader that stores the photos on the disk somewhere and then puts an event in a Kafka queue. I've uploaded a photo. And now somebody else can write a consumer, similar to how you probably wrote a consumer for Kafka, to say, well, whenever a new photo comes in, give me the photo, and I'm running object detection, and I'm writing the results either directly into a database, or in this case, maybe into another stream. And the advantage of this is that you can have many copies of these processes, these consumers, and the number of copies can be different than the number of uploaders here. So when the queue gets long, you could launch a few more of these consumers, that they run more things in parallel, catch up. Or if you're busy, you have few consumers right now, the queue gets a little bit longer. You have that flexibility with these kind of stream processing systems where you can scale somewhat flexibly with demand without having to respond immediately. So you have some buffer in the system. You probably don't want a queue that's 2 or 3 days long and you never catch up. But if it takes 5 minutes now or 10 minutes later, this may be a reasonable design that gives you some flexibility. And you can build these kind of systems where multiple parts independently process the same queue of events at different speeds potentially. You have a friend detection model, an object detection model. They write results at different speeds. Maybe you compute some statistics by reading these results. This again feels like MapReduce, where you reduce the amount of data step by step. You have maybe a notification service that looks at recently detected friends. You have maybe something that writes results to a database. Does this make sense? There are several of these systems, but Kafka is probably the most popular one these days. It scales fairly well. Kafka itself can be distributed massively, that you have these queues across many different machines, can write to many different machines. What's the drawback of an approach like this?
You can have deadlocks if it's constantly writing.
If it's constantly writing, you can have deadlocks. I'm not quite sure, Innocent.
So in the sense, generally when you process using a REST API or something, you're polling for data. So you essentially expect one piece of data at a time. But then with Kafka, you don't exactly know how much data is coming in. You can't estimate that. Yep. So you don't design your DB accordingly, and that would give rise to deadlocks. Like the wrong row could be locked, and then.
Oh, if you're locking something while
Yeah.
writing in a somewhat unpredictable pattern, okay.
Yeah.
That seems like a more specialized problem depending on how you're reading, but yes. A common problem is that you're not just making a call and expecting an answer, but you're thinking in a very indirect way. You're writing something to a stream, and then hopefully somebody is reading from that stream. And if you want an answer back, they're writing maybe into a different stream, and then you can read from that. So it's all very decoupled, and it's easy to have a lot of streams that don't really know who's reading from where. So it's really useful to have these kind of graphs, like which process is reading from what, writing to what. Some of these tools can generate these graphs from you, kind of help you figure this out, how far you're behind, and so on. It's a weird way of thinking in this event-based mechanism that we're not really used to. And you also don't really have guarantees of how long something takes. You're writing something into the queue, and then good luck. I think you had a discussion when you looked at Kafka in the lab about read once versus exactly once or at least once. Did you talk about this in the lab? There's always a problem if Kafka itself crashes or your clients, your consumers crash. What happens to the data that you have just been processing? When you restart, are you indexing the same image again? Like if you do object detection here and the object detection thing crashes, can you make sure that each image has been processed? Or can you make sure that each image has been processed exactly once? There's a distributed system problem here that exactly once you cannot guarantee. You typically have to decide at least once or at most once. So either you decide if something crashes, then you may process things multiple times. With object detection, it's not a big problem. You detect the objects again on an image that you have maybe already done. With processing payments, you don't really want to do that. The alternative is maybe sometimes you miss object detection on an image, which is also fine. The way that you do this in Kafka is how do you confirm that the offset moves forward? There's a configuration setting if you write a consumer. You typically ask for the next data point, and then it either automatically commits, so whenever you read something, it says I've seen the next image, or you manually commit. You need to call a commit function. That means you're reading something, and only when you're done with processing, you commit it. So the offset in the database only moves after you're certainly done with processing. The way that your Kafka streams are set up is only with two partitions. So you can have two consumers in parallel. If you want to try to speed things up, this is the way that Kafka works. You can't have four in parallel, or at least this wouldn't help, because there's only two pointers that can read sequentially. All right. I think this is mostly what I talked about. So you commonly have this design of multiple streams, one process reading from one stream, writing into another. There's stuff that you can do queries over streams, but that's pretty much what we talked about. So for machine learning systems, where might something like stream processing be useful? we had the scenario of inference with Google Photos, right? So you write the photos in the stream, and then you do inference. What are other scenarios where this might be useful?
So they do the behavior in what items they view in the past, and we can change recommendations based on that.
So if you have access to a log file, right, you can see what users have been recently doing. You could stream that and use this for inference potentially, yeah, to change recommendations based on that.
Maybe like security logs or like CMU.
Yeah, anything with logs really. You can write them into a stream and then have something that's processing this. And with security, it's usually maybe you don't need it immediately, but near future, right? Near real time is useful. You don't want to block the system for some of this. I'm going to ask you at some point to update your models in the project for the movie recommendations. So you want to incrementally learn at some point. So you might want to continue running the stream. Additionally, kind of pre-process data, collect training data incrementally. You could do incremental training. Certain models allow incremental training. I don't know about the ones that you're using. SVD doesn't, I think. But a bunch of models provide incremental training where you could do a small update every time new data comes in, right? So continuously learn. Yeah. One more thing that's worth mentioning is this idea of event sourcing or immutable append-only data. If you have a database where you sometimes change data, like you replace the title of a photo or you add some metadata or you delete something, traditional databases just delete the data or modify the data for you. But there is a way that you just log changes. This looks like many small diffs, like a large list of diffs, essentially how am I changing the data over time. So you never change previous data, you just append changes to the end. This is how Mercurial, the version control system, by the way, works internally too. Git doesn't work like this. Git makes copies at different points. This allows you to go back in time in a database, and it only writes to the end. This kind of thing you can process with a stream database too, because you have a stream of changes to your data, and then you have can have a consumer that creates a snapshot and computes what it looks like at any point in time. It allows you to time travel, but it has additional overhead for computing what the most recent version of data is. There's one obvious drawback with doing data like this. Have you seen this discussion somewhere, or is this obvious? Especially when it comes to privacy, the right to be forgotten, similar things. You can never really delete anything. You can only mark things as deleted. Right? So if you actually care about privacy, you can't ever unsee something. It's in your log in the past, create this thing, and then delete it. So that's actually a problem in a lot of settings where you might legally be required to delete things. All right. Have you heard of the Lambda architecture before? This might be useful at least a year, until a few years. This came up in technical interviews quite a lot. This is essentially an architecture that's combining all three things that we talked about just now. It has a speed layer that's a service. It has a batch layer that does long-running computations. And then it has a speed layer is stream processing, and then serving layer that's a service. So it might look something like this. You have a stream of data coming in, live data here. It needs to be append-only data. So if you're making changes, it needs to be in this event sourcing, immutable kind of append-only data. And then you have a stream processing server. So you write it into a queue. You stream process it with incremental updates. This could be incremental updates to a database or incremental updates to a model. So you do incremental learning. or incremental updates, compute something. And then you have a database where all the events eventually go into this database. And then once a day, once a week or so, you run a big process over everything. So you go through your entire history of data to do your computation, to train a full model or collect the data that you need to do. Right, so let's say you want to compute the most popular websites that we had earlier. You can do a batch processing thing that goes over the entire database and computed the most popular websites since yesterday, or until yesterday. And you can do incremental updates then always. If I see another website, increase the counter. If I see another website, increase the counter. Why would you want this combination of these two? Oh, and the serving layer above is essentially just querying your collected database, your cache, or your model. So you're making normal requests. Why would you combine things this way? Why would you combine stream processing and batch processing?
Give it like some more plasticity. So maybe if you're updating most popular websites visited, you're only doing this once a day, but then you leave yourself room to kind of change that as you process the events in the stream.
Right, so stream processing gives you this ability to, in near real time, compute very recent results. Why do you still need batch processing? Why not always compute things incrementally?
It's slow, but it's more accurate.
Why is this more accurate? What makes stream processing inaccurate?
The batch processing look at all the data, but like stream processing, maybe like it needs to look out more than once, so you don't know exactly which one is looking at.
So if you have any problems here in stream processing, you might miss an update or compute something twice, so you might get small inaccuracies. If you do incremental training on models, that's often creating some recency bias, where the things that you've seen most recently, the model will learn that more. Right? It's not the same model that you learn over all data if you first learn it over 90% and then update it with the last 10%. So the idea here is that you do some incremental analysis, which might not be perfect. For example, if there's deletions in your log, you might not process them, you might get duplicate results or so on, but it's fine, it's more fidelity. And then once a day or once a week, you do the full computation again to get the most accurate thing from where you do incremental updates again. Does this make sense? So it's a combination of these, and it requires add-only data, right? Append-only data. It's called Lambda Architecture because it's, I always forget this, because it's like Lambda functions, functional programming, where things are only added, had some meaning. I don't think it's very meaningful, the name. But it's a big buzzword. Any questions on this?
The example we were talking about was like updating model predictions, kind of. Did you say also if this wasn't just for like getting inference answers, were you talking also about like data aggregation?
Yep.
Could you like an example of what that would look like?
So let's say you want to compute statistics like the most popular websites. You can do this incrementally. And the incremental update is probably pretty precise if you implement it correctly. But there might be slack in the system. So I had this example in Strava. It's a running app. Sometimes it uploads things twice. So you get a record immediately over this, and then you delete one of them, and you keep the record for some reason. Because the record best, like personal best record or something like this, computation is not precise over this. But I think it goes away when it could go away when you all recompute it. Right? So there's often things where incremental computations are more complex and they may not fully implement it, or there's some fault tolerance thing that because you can't process everything exactly once, there might be sometimes a mistake. If you don't care about those mistakes or these inaccuracies are small enough, you just do stream processing. You don't need the batch layer. But if you want the whole update once in a while, then you run a batch process. Another example with the most popular websites, you can update this incrementally, but maybe you'd only want to store the top 1,000 most popular websites. So if you do incremental updates there, you don't do incremental updates to less popular websites until they become very popular, because it would be too much storage if you want to do this for all websites. Right? So you do updates to already popular websites, but only new websites come in once a day when they actually are popular, something like this, right? So there might be all kinds of engineering trade-offs. Just briefly, the other buzzword that might be useful for interviews in this context is a data lake, sometimes also called a data swamp. Any idea what that is? Yeah, it's essentially a place where you store all your data, and it's usually not in a very disciplined format. It may have a schema if you're lucky, or it might just be log files where the schema changes every couple of days or so. And the idea is, let's not invest so much effort into data storage now and making it easy to query, because we don't know whether we're going to use it later. But at the same time, data storage is so cheap, maybe that data is useful later. And if it is useful later, we can later figure out how to parse it. So data lakes, in a way, are a bet on the future, that the future yet unknown value of the data is bigger than the storage cost of the data. Right? Storage is cheap. Maybe the data is useful. And let's not invest too much effort into structuring it now. We can pay the price later. And actually, data lake software has gotten much, much better in recent years at also running queries over unstructured data. It's using all kinds of models, LLMs in the background to make sense of your data so that you can query it without a lot of processing and help you with recover data that you care about. The most famous story here is Google itself in the very early days, before they did add keywords. Google was just logging all the searches that everybody did, and it took them several years to realize how valuable it is to have that history of search queries. In the early days, in their headquarters, they had a display in the entry where they would just show live search queries that people were doing, so you could see like what people are searching for right now. And they realized only later, oh, you can learn so much from this. And then they had several months or years of history, including which users searched for what. So it was valuable data that they never really prepared to be analyzed that way, that they had around and used for things. All right. Now I want to bring this together and have you to think about the different designs. So the scenario here is, let's go back to Zulip, and let's say you really want to scale that to a large company. I don't quite know what's built in there. I don't think it's very distributed in itself. But let's say you have over 50,000 users that are using it every day. And you have two features. You have scalable summarization that you implemented. So you want to summarize topics for all your users in the morning or whenever they care about this. And then anomaly detection. So that's kind of a security feature. You need an ML-based anomaly detection thing that finds compromised accounts. So people that behave in a somewhat unusual way in your system, maybe try to leak data or something like this. Right? So essentially look for behavioral patterns. I want you to think about, if you're scaling it in this way, how do you distribute data storage? So partitioning, replication, things like this. How do you design scalable summarization? Service, streaming, batch processing, Lambda architecture. And how do you do this for anomaly detection? Again, service, streaming, batch processing, Lambda architecture. Task clear? Go for it.
Yeah, for how to distribute storage, we will hash the data by user ID as the key, and we'll map the messages as the values. So we'll store it as a key.
So traditional partitioning, kind of.
Yeah.
By user ID, all the data from each user is on one machine.
Yeah.
Might be more useful to do this by topic, honestly, because you're often showing it by topic, not by user. But sure, some sort of partitioning. I think that was the easy part.
Yeah.
How would you do summarization at scale?
Yeah, so for scalable summarization, we could have a Kafka message queue where we are streaming all the messages, and then we could do batch processing. By the time, for example, if multiple users are clicking on summarization at the same time, probably at a 3-second window, then we could summarize so that it looks near instantaneous, but we still are optimizing for processing.
All right, so the user clicks on something, you're writing it into a queue, and you hope that the result comes back in time.
Yeah.
Okay.
And for anomaly.
Wait a second. And batch processing means you're also collecting in some form until you have enough queries or enough summarization requests to do a batch process, or?
Yeah, we are assuming that we have enough queries to batch process, considering we have large amount of users.
All right. Does somebody else have a different discussion for scalable summarization?
I did a lot of squats this morning, and this is a lot of stairs.
So thank you. So when we designed the project, I think what everyone did was you were grabbing summarization from the API at a user level. What if we just grab summarization at a group level, like at a channel level? So for example, you have a channel and like you take the last 5 messages and you summarize that and you store it in some kind of cache. So if that message is unread for me, as a user, I'm not making an API call to the LLM. I just pick up the summary from the cache and I have it already. So in that sense, you're reducing the number of LLM calls. And
so what you're suggesting is some sort of caching at the LLM level, right?
Yeah.
Does it fit into one of those strategies we talked about?
Not exactly, but like it'll help with scalability.
You're still using the LLM as a service, right? Yeah. But just reduced. I'm not sure how much I buy this as a strategy, though, because the summarization is typically in context, right? So you need users to have exactly the same unread messages, right? But you could do some caching, maybe get the input to the LLM faster. Yoda?
It was going to be a microservice.
Can you?
Yeah. So when we designed I1, we had it as a button. So if you're texting like mine, you don't need the summary to go on. If you open it and you have a bunch of messages, you could just call it and it would generate a summary.
Right. So that's kind of what I expected here when I thought of the question, is that you click a button, you want an answer now. Right? You could think about doing batch processing overnight, assuming that everybody comes in the morning and wants a summary. You could pre-compute something like this, but most of the time I think it's something, somebody clicks on this, you want an answer now. You don't want to wait a few seconds or a few minutes, sometimes longer, sometimes shorter. So I think it's a classic service job, right? And you all implemented it as a service, not as a microservice, but as a service, as an immediate call. For the last one still, sorry. I have more. Anomaly detection. What did you talk about there?
For anomaly detection, I guess we can just do, we can have a more intelligent way of flagging accounts without machine learning. So you have a way to kind of drastically scale down the amount of accounts you do the machine learning based anomaly detection on. So for example, you can have a static algorithm determine which accounts are suspicious, and then of those suspicious accounts, you can either run them out through the algorithm, or in case of a bottleneck, you can just select randomly sample a subset of that. And also in addition to that, if it's tagged that, we can also tag it on like kind of an urgency level. So if like something is suspected of it being a compromised account or anomalous account, but like fixing it isn't a very high priority. For example, if it's like it's been inactive for a long time, we can also schedule the algorithm we can also schedule the model to run on it, to like, for example, in the middle of the night or at a point in time where we're not receiving a lot of requests.
So have you thought about whether you would use stream processing, batch processing, service, Lambda architecture?
Not too sure. I don't know.
Okay.
Yeah, so we could use like a hybrid approach here, depending on what we want. And in implementation, we might have some logs that are important, and if we have any times that then you would use things. You would use streaming like Kafka, but then there might be other things that you would upload at night. Then you would use batch. So that's how I like. You don't want everything to run like in streaming, right? But you don't want everything to be only on night.
Do it based on load or based on demand, kind of?
Yeah, I mean, given that it's Zulip, we have the nature of data, there might be things that get uploaded progressively, and we want to detect that every 5 minutes. Okay. But there might be other things that are probably makes more sense to do it only overnight.
So my intention behind this was to have an example where the Lambda architecture makes sense, although I've been thinking more about training than inference. Right, so if you have an anomaly detection model, you have all kinds of behavioral data that's coming in, and you train your model, and you want to update this on more recent patterns too. But it may be useful to once in a while train the model on all behaviors, not on the most recent ones. And then for actually inference, yeah, I don't know, you could do this as batch processing overnight or on a clock or something, or put everything in the stream. It doesn't really matter, I guess, that frequently how you run it. But the idea was here to give you an example where the Lambda architecture would make sense, but probably more on the training side. Right. So with this, I think that's a good place to end up. I just wanted you to give you a really brief overview at how to deal with large amounts of data, large amounts of computations, and any form of distributions. I think the distinction between stream, batch, and service processing, and also the Lambda architecture is useful. How to actually implement it, what technologies to use, you have to figure out. We're showing you some in the lab, but this is what I wanted to convey today. All right. See you here on Wednesday for a midterm.